title of my talk is Changes in Yolk weight, water, organic and inorganic content of Octopus vulgaris type 2 eggs during embryonic development. As you notice, the title is a little bit different from the one that's in the abstract, and I will explain the reason for that later. So, in environmental conditions play an important role on egg and larval quality. More information thus is required on how environmental factors can be manipulated during embryonic development for the production of high-quality offsprings. Temperature influences both the efficiency and the rate of yolk utilization of embryos and hatchlings. We know from the literature, especially squid, that the higher the temperature, the shorter the duration of the survival time of unfed hatchlings. So, sorry for that. So how incubation temperature affects the yolk reserves that will be available for Paralarvae hatching? This is the main questions that I will try to answer or address during this talk. This will impact the survival of Paralarvae during the critical transition period from yolk absorption to successful prey capture. So the objectives is to evaluate changes of water, organic and inorganic content of Octopus vulgaris type 2 eggs at 24 degrees C, and to relate these changes to yolk utilization of embryos and survival of starved Paralarvae at 19 and 24 degrees C. So egg samples were taken every other day during the whole embryonic developmental time. That is at day 1, 3, 5, 7, and so on, to the hatching of Paralarvae. 150 eggs were randomly sorted from the mother's den. These eggs were separated in 15 samples of 10 eggs each for obtention of wet weight and dry weight. The water content was obtained by subtracting dry weight from the wet weight. Ash-free weight was also obtained, and then we obtained the organic content by subtracting ash weight from the dry weight. All these measurements were follow the methodology of Omori and Ikeda 1984. So for the yolk volumes, we obtained images of 50 eggs collected every other day, also from the whole embryonic development. These estimated yolk volumes were converted into yolk weights by the methodology of Vidal et al. 2002, and we also obtained the ratio of yolk weight to hatchling wet weight, that is the percentage of yolk in relation to the wet weight of the Paralarvae at hatching. Survival of starved Paralarvae was obtained by two simultaneous culture of unfed hatchlings at 19 and 24 degrees C. They were culturing 200-liter tanks, each one with 300 Paralarvae each. So, the first stage of development, the yolk was measured with an elliptical shape. Then, at stage 13, on day 11th, it's the beginning of the formation of the internal yolk sac. So the external yolk is being internalized, and the yolk was measured by an elliptical and a cylindrical shape. It is in this stage that organogenesis starts. So you can see here the first inversion of the embryo. Okay? And after this period, we clearly can see a connection between the external and the internal yolk sac, so that the volume was estimated by several forms, geometric forms. After this stage, stages 16 and 20, we could not see clearly the connection between the external and the internal yolk sac. So during this period of time, we underestimated the amount of yolk because we couldn't see the connection between the internal and external yolk sacs. And close to hatching, the internal yolk sac is fully absorbed, and there is no more, when there is no more yolk visible among the arms, it's the embryo hatched, and here we have the newly hatched paralarvae with no external yolk among the arms. When this happens, we have a premature hatching. So, in summary, when we look at the whole data set for the whole embryonic development, in this axis we have wet weight, and here we have yolk weight, and we can look at here embryonic developmental days, and we can notice that during the first 7 days, the wet weight doesn't change much. It remains nearly constant until the 7th day. It's after the beginning of the organogenesis here, from day 9 onwards, that the wet weight starts to increase at an exponential rate. That means that the eggs are absorbing water, right? In relation to, so there was an increase of 68% in the wet weight during the whole embryonic development. In relation to the yolk weight, we see a similar tendency during the first 7 days. The yolk weights remain nearly constant. It's also after the beginning of the organogenesis that we see a pronounced decrease, an exponential decrease in the amount of yolk because of the formation of the embryonic tissue. It's used in the formation of the embryonic tissue, but some yolk remains for representing the internal reserves of the paralarvae. So the decrease in yolk was around 48% during the whole embryonic development, and at hatching, 20% of the paralarvae wet weight was represented by the yolk weight. In relation to dry and organic weight, we saw there is no variation, no main variation during the whole embryonic development. Dry weight remained nearly constant. Organic weight decreased 12%, and we notice that the ash-free weight represented around 3 to 5% of the dry weight of the eggs. In relation to the paralarvae, these are hatchlings that were separated into 2 groups, one maintained at 24 degrees in yellow, and the other one at 19 degrees in blue. And even though wet weights are very variable, we clearly see that there was, as expected, reduction in the wet weight of the paralarvae maintained at a higher temperature, suggesting that the yolk was absorbed very fast. Even though wet weight didn't change much, when we look at the survival rates, we clearly see that nearly 90% of the population died on day 12 for those maintained at 19 degrees, but 4 days earlier, at day 8, for the population maintained at the survival time for those paralarvae that didn't eat was much shorter at a higher temperature. Well, what is very simple data is showing? Basically, it shows that the absorption of water during embryonic development is not constant. It increases dramatically at the beginning of the organogenesis, and this has implications for absorption of salts, metals, and contaminants into the embryo during the embryonic development. Wet weight increases 68% during development. Yolk, the water content ranged between 70 and 80%, similar to the adults, that's around 82%. Yolk weight decreases 48%, and this was related to the formation of embryonic tissue and also respiration. Higher yolk content in hatchlings maintained at 14 degrees than at 18 degrees were also found by Nandi et al. 2017. Organic weight and dry weight were nearly constant throughout development, similar to the results found for C. officinalis by Bouchard and Dubouzin, 1990. And the yolk weight to wet weight ratio represented around 20%, what seems to suggest that yolk was efficiently converted into body tissue even in this high temperature of 24 degrees. This result is similar to what was found for the squid oligopalescens. This ratio was around 10 to 15%. So, in conclusion, water and yolk absorption are not constant during the whole embryonic development. It increases drastically during embryogenesis, and water content increases and yolk absorption decreases after organogenesis. Paralarvae should be maintained then at lower temperatures at hatching to reduce their later yolk utilization and increase their survival potential during the critical transition period from yolk to successful prey capture. This has direct applicability to aquaculture, as we want to reduce as much as possible the high mortality rates that follow soon after hatching. Also, higher temperatures will certainly produce paralarvae with reduced yolk reserves and increase their likelihood of malformation and mainly premature hatching. So this has direct consequences to global warming scenario. We have analyzed the data. I have shown here today the data for the temperature of 24 degrees C. I have changed the title of the presentation because I was not able to finalize analyzing the data we have for 28 degrees C. That will help us to understand exactly how yolk is absorbed and the energy from yolk is transformed or into somatic tissue at such a high temperatures. The high metabolic demand of embryos maintained at the higher